Today we are going to learn about hyperparameter tuning in support vector machines. We'll explore how to optimize the cost and gamma parameters to enhance the predictive power of SVMs using techniques like grid search and cross-validation. By the end, you'll acquire essential skills for effective hyperparameter tuning in real-world applications. Welcome to our session on hyperparameter tuning in support vector machines. Hyperparameters are crucial elements that dictate the performance of SVMs. Unlike regular parameters that are learned from the training data, hyperparameters are set prior to the training process. Tuning these parameters, especially the cost, C, and gamma, can significantly enhance the model's predictive accuracy. In this video, we will delve into the significance of these hyperparameters, learn effective tuning strategies, and understand their impact on model performance. By the end, you'll be equipped with the knowledge to implement these techniques in real-world scenarios.
Support vector machines, or SVMs, are powerful supervised learning models used for classification and regression tasks. At their core, SVMs aim to find the optimal hyperplane that separates data into distinct classes with the maximum margin. The role of hyperparameters in SVM is pivotal. They govern the model's complexity and the decision boundaries' flexibility. Understanding the hyperplane's role in SVMs provides insight into why hyperparameters like and gamma are critical. These parameters influence how well the model generalizes to unseen data. SVMs are favored for their robustness in high-dimensional spaces and their effectiveness in handling nonlinear boundaries through kernel functions.
Hyperparameters in SVMs are predefined settings that shape the model's learning process. Unlike model parameters, which are learned from data, hyperparameters are set before training begins. They dictate the model's structure and learning capacity. The cost parameter, C, controls the trade-off between maximizing the margin and minimizing classification errors. A small c creates a wide margin but allows some misclassifications, potentially leading to underfitting. Conversely, a large C focuses on classifying all training examples correctly, which may cause overfitting. The gamma parameter defines the influence of a single data point. A low gamma implies a broader influence, while a high gamma captures more detail, impacting the model's decision boundaries.
The cost parameter, denoted as C, is a crucial hyperparameter in SVMs that determines the trade-off between maximizing margin width and minimizing classification error. A smaller C allows for a wider margin, which might include some misclassifications but can enhance generalization. This approach reduces the risk of overfitting. On the other hand, a larger C focuses on classifying all training points correctly, which might result in a narrower margin and increased risk of overfitting. Choosing the right C value is pivotal to achieving a balance between model complexity and accuracy. This decision significantly influences the model's performance and its ability to generalize to new data.
Gamma is another critical hyperparameter in SVMs, particularly influential when using the radial basis function, RBF, kernel. It defines the influence range of a single training example. A low gamma value implies a broader influence, which can lead to a smoother decision boundary. This might cause underfitting if the data is complex. Conversely, a high gamma value results in a more detailed boundary, which could lead to overfitting as the model might capture noise in the data. Balancing gamma is essential to ensure that the model captures essential patterns without being overly sensitive to noise, thereby optimizing its predictive performance. The interplay between hyperparameters like C and gamma significantly affects an SVM's performance. These parameters dictate the model's ability to generalize from training data to unseen data. A well-balanced combination of C and gamma can optimize the model's accuracy and generalization capabilities. High C values might cause overfitting, while low values might lead to underfitting. Similarly, gamma needs to be balanced to ensure the model captures the right complexity level. By analyzing the model output, one can adjust these hyperparameters to strike a balance that improves accuracy without compromising generalization, ultimately leading to a robust and reliable model. Grid search is a systematic approach to hyperparameter tuning that involves specifying a grid of possible parameter values. The method exhaustively searches through this grid to identify the best combination that optimizes model performance. By automating the search process, grid search simplifies the task of hyperparameter tuning, allowing for a comprehensive exploration of potential parameter values. When combined with cross-validation, grid search provides a robust framework for evaluating different parameter settings, ensuring that the selected combination maximizes accuracy while maintaining generalization. This approach is invaluable for practitioners aiming to fine-tune their SVM models for real-world applications.
Cross-validation is a critical technique for assessing a model's performance and ensuring its robustness. By splitting the dataset into multiple subsets or folds, cross-validation allows for a more comprehensive evaluation of the model's accuracy and generalization capabilities. Common strategies include k-fold cross-validation, where the data is divided into k subsets, and leave one out cross-validation, which uses a single instance as a test set while the remainder forms the training set. Cross-validation is especially useful in hyperparameter tuning, as it provides insights into how well the model performs with different parameter combinations, thereby reducing the risk of overfitting and ensuring reliability.
Python offers a plethora of libraries for hyperparameter optimization, making the tuning process more efficient and accessible. Scikit-learn, for instance, provides built-in functionality for grid search and cross-validation, allowing users to seamlessly integrate these techniques with SVM models. Other libraries like Optuna and HyperOpt offer advanced optimization capabilities, enabling practitioners to explore parameter spaces more effectively. These libraries simplify the implementation of hyperparameter tuning, providing intuitive interfaces and robust algorithms. By leveraging these tools, data scientists can enhance their model's predictive power, ensuring optimal performance in various applications. Hyperparameter tuning presents several challenges that practitioners must navigate to achieve optimal model performance. Identifying the right combination of parameters requires a deep understanding of the model and the data. Overfitting is a common concern, as overly complex models may capture noise instead of essential patterns. Balancing model complexity with generalization is crucial to avoid poor performance on unseen data. Large datasets can exacerbate these challenges, making tuning computationally intensive. However, by employing systematic approaches like grid search and leveraging cross-validation, practitioners can overcome these hurdles, optimizing their models for accuracy and reliability.
To illustrate the process of hyperparameter tuning, let's consider a case study involving a sample dataset. This dataset contains various features that need to be classified using an SVM model. The tuning process begins by defining a grid of possible values for the cost and gamma parameters. Using grid search combined with cross-validation, we systematically evaluate different parameter combinations to identify the optimal settings. The results demonstrate significant improvements in model accuracy and generalization. This practical application highlights the importance of hyperparameter tuning in real-world scenarios, offering valuable insights and lessons for practitioners aiming to enhance their model's predictive power.
As we conclude our session on hyperparameter tuning and support vector machines, let's recap the key points. We explored the critical role of hyperparameters like cost, C, and gamma in shaping an SVM's performance. Tuning these parameters is essential for enhancing the model's predictive power, ensuring it generalizes well to new data. Techniques like grid search and cross-validation provide a robust framework for identifying optimal parameter settings. By applying these strategies, you can significantly improve your SVM model's accuracy and reliability. We encourage you to implement these techniques in your projects and witness the transformative impact of effective hyperparameter tuning.